So far we learned that if you have 2 points in the space, you can connect them together and you can create some new mathematical object that we call a vector. So let A with coordinates x sub 1, y sub 1, and z sub 1, and the second point B x sub 2, y sub 2, and z sub 2 be 2 points in this space. Very well. We can define a mathematical object that has the direction and the magnitude. So suppose you start from point A and you're reaching out to point B. They have the initial point A and they have the terminal point B. We can construct this new mathematical object AB, which is defined as, well, instead of using parentheses, we're going to use a new set of symbols that represent this new object. Vector. The terminal point has x sub 2, y sub 2, z sub 2, so they come first. X sub 2 minus x sub 1, comma, y sub 2 minus y sub 1, and finally z sub 2 minus z sub 1 is this new mathematical object that we call a vector. Starting from point A and going to point B in this direction. Very well. So as you saw, the magnitude of this vector is defined as, so the magnitude or norm or length using AB with a small bar on top of it representing the vector is equal to, here we have the square root of, we take each component of the vector and raise them to the second power. Then add all together. So x2 minus x1 squared plus y2 minus yy squared plus z2 minus z1 squared. As you can see here, we have square root, and this is the magnitude or norm or length of this vector. So why do we need a vector? Suppose you have a plane in the sky. So there is a path that plane forms in the sky. You might be interested in associating a vector, or in more technical form, a vector function to the path of that plane in the sky. Vectors and eventually vector function help us to define that path in the sky. Very well. So now that we define this new object, we're interested in defining some mathematical operations that can be done on those objects. How do we add them? How do we subtract them? Well, how do we define something like multiplication between vectors? So this is our goal. Our goal is to define mathematical operations between vectors. So suppose you have two vectors. let u and v be two vectors. First of all, we can take these two vectors and add them together. So suppose u is defined as x1, y1, z1, and v with its components x sub 2, y sub 2, and z sub 2. So u plus v is defined as a new vector. Well, the components of this new vector is the addition of the components of u and v. So it's defined as x1 plus x2, y1 plus y2, z1 plus z2. Well, how do we do subtraction between two vectors? U minus v can be written as u plus -1 times v. Here, what are we doing? We are multiplying a scalar, a number like -1 by v, and then add these two vectors together. So here you have x1, y1, z1 plus -1 times x2, y2, z2. Here we are using scalar multiplication, scalar and a vector. This is equal to x1, y1, z1 plus, well, we distribute this -1 into the components of the vector. -1 times x2, -1 times y2, and -1 times z2. So we have minus x2, minus y2, and minus z2, which is equal to, well, now we are taking the first components, taking the second components, and the third components, and add them together. We have x1 minus x2, y1 minus y2, and z1 minus z2. So as we mentioned, we have scalar multiplication. So suppose R is just a number, a scalar. Scalar, which is nothing but a number. Then we can define R u, which is R, and vector u, x1, y1, and z1. So as I mentioned, in a sense, you're distributing R, your scalar, into the components of the vector. So here you have a new vector, R times x1, R times y1, and R times z1. Let's go over some examples to feel more comfortable about these operations between vectors and scalar and a vector. Example. Well, in this example, we have the following. Vector A is given to us as 4, 0, 3, and the vector B, the second vector, is -2, 1, and 5. Well, the question says, find the magnitude of vector A, then construct A plus B, then construct A minus B, find 2a plus 5b. Very well. First, recall that if a is a vector like x, y, and z, then the magnitude, norm, or length of the vector is defined as the square root of x squared plus y squared plus z squared. So let us take these components of the vector a, raise each to the second power, add them together, then take the square root. We have 4 squared plus 0 squared plus 3 squared, which is equal to the square root of 16 plus 9, or the square root of 25, or 5. The length, norm, or magnitude of this vector is 5. B, it says, well, what is the addition between these two vectors? We take the components of the first vector, 4, 0, 3, and we take the components of the second vector, add them together. So here we have 4 minus 2, comma, 0 plus 1, comma, 3 plus 5. Here we have this new vector with components 2, 1, and 8. Well, you might be interested in visualizing the sum between these two vectors. So to visualize the sum of these two vectors, we can graph these two vectors. Okay, let's take a look at this. Here we have our x-axis, here we have our y-axis, and here we have our z-axis. Very well, our first vector, 4, 0, 3. So 1, 2, 3, 4. Your y is 0 and your z is 3. 1, 2, 3. Very well. So our vector originates from 0, 0, 0, or from the origin, and this is your vector. Vector A. For the second vector, vector B, we have minus 2, very well, so we're going to be on opposite side of x-axis, negative 2, so here we have our minus 2, then we have y equals to 1, so minus 2, and y is 1, and our z is 5, 4 and 5, very well. So here we have our second vector. One up to 5. And then here, if we connect these two together, we're going to have this guy goes up to 5 here. 2, 1, and 5. There we go. And our final vector, this is vector B, which is the sum of these two vectors, is going to be, okay, we can use the parallelogram method and have the vector B starting from the terminal point of vector A in the same direction, parallel to vector B, with the same magnitude, and then at the end point we're going to have our sum of two vectors, which is this new vector here, A plus B. So in this method, in parallelogram method, here we have vector, for example, u, and we have vector v. You can use u or v, it doesn't matter because it's addition. So we're going to take vector u and take the exact same length parallel to vector u. We're going to continue, and here we can also start from the terminal point of vector u and use the same magnitude parallel to vector v. And then here you have a parallelogram. Its hypotenuse is going to be the sum of these two vectors, u plus v. Very well. What about the subtraction between these two vectors? For the subtraction, as you remember, we're going to subtract the components correspondingly. So here we have 4, 0, 3 minus negative 2, 1, and 5. So it's going to be equal to 4 minus minus 2, 4 plus 2, 0 minus 1, and finally 3 minus 5. Very well, the outcome is 6, negative 1, and minus 2. The subtraction between these two vectors. And finally, what if I multiply the first vector by 2, the second vector by 5, and add them together? Very well, here you have 2 times the components of vector A, 4, 0, 3, plus 5 times the components of vector B, second vector, negative 2, 1, and 5, which is equal to, so we're going to distribute 2, then distribute 5, and add the components together. Here we have 8, comma 0, comma 6, and then negative 10, 5, and 25, which is equal to, here we have 8 minus 10, negative 2, 0 plus 5, 5, and 6 plus 25, which is 31. In all cases, we constructed a new object by adding, subtracting, using scalar multiplication and addition between two vectors. Another method representing a vector is using standard vectors. For each axis, x, y, and z, we're going to use some nice vectors that represent those axes.